I drove home and I sang songs the entire 4-hour drive. Coming back from here, it was I could not talk for a week. And it sounded like I had COVID. It was horrible. I hated it.
How other people struggle when they get COVID, like they isolate, and so I know people who've gotten it, and then they just don't say anything, and I can't blame them.
See, if I get it, I'm getting that 400. Yeah, exactly.
Yeah, if you want your gift certificate, right? Like,
I see how you covered my good.
I mean, what, $500 at the bookstore is what, like one book?
They have electronics there. I could get a discount on something.
Oh, there you go.
That might work. So,
all right.
I'll find a way to make a profit.
All right, so today, let me start recording here in a second. I clipped the beginning of this off when I put it up. Yep, okay. All right, so today we're going to talk about section 10.2, which is about the introduction of calculus to parametric curves. And we're going to use a lot of the engineer's trick on this one, which is pretending the dy dx is a fraction. So remember the last time, we defined what we meant by a parametric equation, which you can think of as being x is a function of t, y is a function of t, and then we think about the curve generated by these functions as being the set of coordinates that you get by sticking these together, right? So the curve C is a parametric curve given by ft here. At any point on the curve, you have coordinates x, y, some of the basic concerns we have here are the same concerns that we had in calculus 1, calculus 2, which is I'd like to be able to, for example, draw a semi-accurate graph of this thing, which requires having descriptions of things like its tangent lines. Where are the tangent lines? The slopes of those tangent lines? Where are the critical points? Where is the concavity change? I want to be able to recover all this information from the graph by looking at f of g and t of, and g of t. So I don't really want to have to eliminate the parameter to do that. So I want to study this picture. The goal is we want to study the curve C with calculus. And so you can imagine some of the questions that we've had in the past that we studied with calculus are things like tangent lines, concavity, arc length, area. These are all things we use calculus to get, but all of them in the prior version of this required that we had y as a function of x. We needed this when we learned this the first time. And I don't want to have to take a parametric equation and eliminate the parameter to do calculus on it. I just want to do calculus on the pieces I've got. So that's what we're going to develop is ways of thinking about how derivatives and integrals work in the case where we don't have this. So instead of y is equal to f of x, instead we're going to be looking at g of x, y is x is equal to f of t and y is equal to g of t. This picture, what calculus looks like here, derivatives and integrals in this setting. That means I get to use my favorite engineer's trick. So what is the trick of engineers? Well, clearly, if I write down something like dy dx, this is a fraction. There's some way to make this rigorous where you think about it in terms of differentials or whatnot, but it's a fraction. The way engineers think about that. I'll talk about symbols that you can manipulate like a fraction. So one of the manipulations that you might do is we're just going to assume things and then assume that they're true, do some manipulations, and then we're going to get the result that we want. And the fact that we found a good result means that we're justified in having made the original assumption, like backwards mathematics. So let's assume that f of t and g of t are differentiable. I mean, essentially, if we don't have the coordinate functions being differentiable, then there's no point in trying to do calculus on it, right? So they have to be differentiable functions to start with. And we're going to make one additional assumption that isn't necessarily obviously warranted, which is we're also going to assume that y is a function of x. You should be leery of this assumption because we just pointed out last time, most of the time a parametric curve is not y as a function of x. In fact, this is very obviously not because it fails the vertical line test, right? So what justifies this assumption? Let me give you one of the ultimate mathematical cop-outs, which is true. This is actually the way pure mathematicians think about this. As long as you restrict your vision small enough, you make a small enough box around any point that you choose, y looks like a function of x. And the weasel word mathematicians use is locally. So what we're going to say is, okay, this is not a function. This is not y equals f of x. But if you zoom in real close, you would have a picture that looked like this. So as long as locally, that is, if you restrict your vision enough, y is a function of x as long as you look tight enough, right? So that's what justifies the assumption that y is a function of x here, is that we can always zoom in onto some little window where we just actually have a function. Now, the only other case we have to worry about is where the thing crosses itself. It's also possible that we could have curves that go like this. And there's no way to make that point into a function of a point where it's a function. But instead, we cheat and think about it as a function that looks like this, and another function that looks like that sort of just cross over the top. So we sort of pull it apart. So in fact, this function is going to turn out to have two derivatives at this point. One for each of the lines that intersect this point. Okay. But when we're thinking about these things being differentiable, what we're imagining is that we're looking really close to some point so we can actually write y as a function of x. And the reason that you want to do that, I mean, of course, if you're an applied mathematician or a scientist or an engineer, you're totally happy making assumptions like that because it means you can do this. Well, if y is equal to g of t, and also y is equal to some function of x, y is a function of x, and x is a function of t, use the chain rule. If y is a function of x and x is a function of t, y is also a function of t, you could write dy dt, well, the t derivative of y by the chain rule is going to be equal to the x derivative of y times the t derivative of x. So the mathematical justification for this is the chain rule. So the mathematician says the chain rule gives you this equality. This is just the chain rule. The engineer says that's true because the dx is canceled. Right? I mean, there's dx down here and dx if you're like cancel, dy dt. All I did was I uncanceled dx on top and bottom. However you arrive at your conclusion that this equation holds, that gives you an expression for dy dx, which is the slope of this thing. You can imagine at any point, the slope of that line is still dy dx, change in y over change in x. But this gives you a computational formula for dy dx in terms of dy dt and dx dt without eliminating the parameter. Dy dx is equal to dy dt divided by dx dt. Or if you like, the engineer's approach, well, I could just uncancel a 1 over dt out of each one of these things and I would get the same formula. So what this says is, I can compute slope without eliminating the parameter. Which is nice. There's no algebra. I can work purely in terms of f of t and g of t, the functions that give me the dx and the dy. We're going to do an example of this in just a second. In fact, let's start with this one. And then we'll talk about the second derivative. So suppose f of t is equal to t cubed minus t. Let's say 3t. And let's say g of t is equal to t squared. Find y dx as a function of t. What the formula says is, well, I could eliminate the parameter by gluing these things together. I'm not going to want to because I'd have to put t is equal to root g and then put the root g up here, get some sort of nasty like root-based algebraic expression that relates these two guys. Or I can write dy dx is dy dt over dx dt, which gets you 3t squared minus 3 over 2t. So I can work entirely in terms of the parameter. And you could really think here, this is a function of t, right? I mean, what we're doing is we're saying for any point on the curve given by a time that I've chosen, whatever fraction comes out here tells you what the slope is at that point. Make sense? Or no, I'm getting some confused looks. Have I made a bad derivative somewhere? Because I do that occasionally. I don't think so. Okay, I guess we're thinking here that, oh, I have this backwards. No, sorry, this is supposed to be y, which is g, and this is x, which is f. There. I apologize. That was my mistake. So if the y is given by this function and the x is given by this function, then the derivative is given by the y derivative divided by the x derivative. Okay? Now the advantage to working this way is now I can work entirely in terms of the parametric equation. So we can answer all these first derivative questions with this idea. Where does this thing have horizontal tangent lines? Where is C, which is given by f of t, g of t, flat? Say, has horizontal tangent lines. Well, if this was a regular old equation and I said, where is the tangent line horizontal, what equation would you solve? Way back to calculus 1 here. Derivative is 0, right? Derivative is 0 corresponds to horizontal tangent lines. So we solve dy dx is equal to 0. But I can replace dy dx with this one variable family or this one variable function. This equation is the same as this equation. That happens whenever t is equal to 3t squared minus 3 is equal to 0. So t is plus or minus 1. Now that doesn't tell me the points that it happens at. It tells me the t values that correspond to those points. So if I actually want to know where on the, this is building towards constructing a graph of what this curve looks like, right? So we don't just need to know the parameter, we need to know what points it corresponds to on the graph. Okay? This tells me the parameter that happens that forces the derivative to be 0, but it doesn't tell me the actual coordinates of the points that happens at. If you want to do that, you've got to take these time values and plug them into the x and y formula to figure out the points. So at t is equal to 1, x, y is equal to what, 2? No, 1, sorry, 1, right? 1 minus 3 is negative 2. I think.
Yeah.
Because I'm using these formulas right here. Remember, x is equal to t squared and y is equal to 3t cubed minus 3t. At t is equal to -1. So I put no restrictions on time. We can imagine this time as time is flowing from -infinity to positive infinity, flowing forever. If t is equal to -1, we end up at the point 1, comma, so -1 goes in, turns into a -1, but then we add 3 instead, so we get positive 3. So what we're doing is we're collecting points that we can use to construct a graph. So horizontal tangent lines for this thing occur at the point 1, 2, and 1, -2. And if I want to put little horizontal tangents there, remember that's how the curve is going to go when it hits these points, right? It's going to have to do something like this, here and here. I guess it's possible it could be up here instead, I don't know. But whatever it does, it's going to brush it like this. What else would be nice to know? Well, let's see. What happens at the point, let's look at the point 3, 0. What is the slope at xy is equal to 3, 0? So this is an example, so I'm giving you a special point here so you don't have to discover it on your own, right? You shouldn't think that this is something you just eyeball, just given as part of the problem. Okay. So at 3, 0, well, that's going to happen when x is 3 and y is equal to 0, right? So let's actually go look and see what values of t correspond to having a 0 in the y-axis. That's actually going to give us the x-intercept, right? The x-intercepts are going to happen when y is equal to 0. So let's solve that. Y is equal to 0 happens when t cubed minus 3t is equal to 0, which happens when t times t squared minus 3 is equal to 0, which happens when t is 0, or t is √3, or t is minus √3. So these three values of t give you a y-coordinate of 0. Here I've used this equation, not the derivative, but this equation. Make sense? Finding x-intercepts is typical. But notice, I haven't actually found an x-intercept yet because I just know parameter values. I don't know the x-coordinates of those points. So we have to compute and see what the x-coordinates that go with these things are. The y value was 0, which corresponded with these time values, which means we actually have to go compute. Well, x of 0, we can think of as being 0 squared, which is 0. Okay, so that point is on the graph. That's a point on the graph, not a derivative, because I'm working with the x's and the y's. When I put √3 into the squared function, I get out 3. But when I put in minus √3, I also get out 3. Two different time values of this moving particle give me the same point on the graph. Two different time values give me the same point on the graph, which means there's going to be a crossing point right here. The function, it's sliding through that point twice, right? Two different time values at the same point means the curve must touch itself somehow. It's wrapping back around somehow on itself. So this point right here happens twice. And what are the slopes at those at that point? Well, dy dx is equal to 3t squared minus 3 over 2t. And I think if you compute this at √3, this is going to be a 9 minus 3, which is 6 over 2 √3, which is positive √3. And dy dx of minus √3 is going to be 6 over negative 2 √3, which is minus √3. So we're computing slopes now, not points, but slopes. So that means as I come through this point at negative √3 seconds, my slope is negative, and then I do whatever I'm doing, and when I get back there again, when t is equal to positive √3, my slope is also √3. So what's going on in the graph? As I come through, as time flows, I'm coming through the graph with the slope of what, minus, so it's like this. This is maybe, what is minus root 3, 1.7? So we can think there's a slope minus root 3 tangent line to that point. And also, there's a slope positive root 3 tangent line to that point. So this thing is definitely crossing through in an X here. Right? This curve is self-intersecting. Okay, so far? All right. Well, now what do we, I can actually guess right now at what this curve is doing. And I'm going to. Right? So when I'm coming down to this point as time goes to, so the slope has to be negative. The slope of this graph is negative when time is equal to minus root 3. And this is the negative slope line right here. So I think this is what's happening. I come into the point on the negative slope line. I cross over and I touch this point up here. What was the t value for that point? -1. That point was located at minus root 3. This point was located at t is equal to -1. When time was equal to 0, I was at 0, 0. So this is the t equals 0 point. And I bet I come back around to the t equals 1 time and then come out like this. I bet that this is what this curve looks like. This would contain all of the information that we have so far. It hits the t equals 1 point, the t equals 0 point, sorry, the t equals -1 point, the t equals 0 point, the t is equal to 1 point, and then that point happens twice, both at -3 root 3 seconds on the way in, and then positive root 3 seconds on the way out. So the direction along the curve is going to be like this. Also, part of drawing one of these graphs is making sure that you have the direction of motion correct as well. Okay, that's pretty good, right? So let's draw this a little bit more cleanly. And if I did so, I would get 0, 0, 0. What are the other 2 points? 1, 2. 1, -2. And I think I'm going to come in like this, touch, down, and out, perfectly symmetrically. -1, 0, +1, root 3, and I came in, sorry, I go out at root 3, and I came in at t is minus root 3. You want to try to be steady, like make sure that you've got information here that makes you believe you've got this correct, right? So locating the points at a particular position of time is a way of being consistent about the way that you're doing this graph. Of course, this is not where we stopped when we learned calculus 1. Because we also needed to know about concavity, points of inflection, right? Remember that the whole reason that you all probably had the feeling that the entire reason they taught you the second derivative was just to force you to draw graphs. So how do I compute concavity of this thing? I mean, the way I've drawn it, it sure looks like there's a point of inflection that happens right here, where it's concave down over here and concave up from this point forward. How can I prove that? How can I prove? Don't shake your head at me. How can I prove that 0 is an inflection point? What do I need to compute? Second derivative. What am I going to do with it? That equals 0. I know that I'm probably dredging up bad memories here, but we also want to know about concavity. Now, we're being abstract and mathematical here, but remember in a physical setting, what we're talking about is the first derivative is really measuring, if we think about this as a particle, the first derivative is measuring velocity of the particle. And the second derivative is measuring the acceleration of the particle. So there's physical meaning attached to these derivatives as well. Okay. So it's not just an exercise in drawing accurate graphs. So the problem is, I need a formula for the second derivative. That's the issue. So let's go back here again. dy dx is equal to dy dt over dx norm. So we're going to use the engineer's trick again. We're going to say, well, one way to think about the second derivative is it's the derivative of the first derivative. That's what a second derivative is, right? So I'm going to write this instead. D by dx of y is equal to d by dt of y over dx dt. I can put anything I want in where that y is and get a meaningful statement out. So I'm going to, instead of y in there, I'm going to put dy dx. A reasonable thing to do. So if I substitute the y out of the first derivative formula, I get the second derivative formula. And be careful because it is not the second derivative of y over the second derivative of x. It's more complicated. What you really like this to be is, oh, just take another derivative up here and divide by another derivative down here. It's more complicated. When you do the substitution of this formula, you get d by dx of dy dx equal to d by dt of dy dx over dx dt. Notice that didn't move, right? The dx dt down here is the same. So I've substituted out the y and put the first derivative in its place. And so we get a formula for the second derivative, which is d2y over dx squared is equal to, and there's really no way to make this any simpler, d by dt of dy dx over dx dt. Be careful. This is not equal to y double prime over x double prime. Big warning there. Common mistake. I had made it myself in lecture a long time ago when I thought I could give lectures without preparing because it's just calculus. Okay. So I would like to know where this function changes concavity, which I suspect happens right here. So I'm actually going to compute the second derivative. So the computation of the second derivative in this case, what was dy dx again? Dy dx in its parametric form was 3t squared minus 3 over 2t. Now, I'm going to have to take a t derivative of that, and I hate the quotient rule. So I'm actually going to rewrite this as 3t minus 3 over 2t. That's okay. 3 halves. Right. There. Better. Okay, so what is d by dt of dy dx? What's the derivative of this guy? 3 halves plus 3 halves 3 over 2t squared. The t derivative of the first derivative. Make sure you check me to make sure I don't make mistakes on this stuff. I think that's right. You can think of this as also being 3 halves times 1 plus t squared. But I also need to, if I'm going to compute the second derivative in terms of y and x, I need to divide that by dx. Yes. I guess there's no reason not to just leave it that way. Okay, so that means that dy dx, second derivative here, d2y over dx squared is equal to this thing, 1 plus 1 over t squared divided by dx dt, which was 2t. So that's the full second derivative. d by dt of dy dx divided by dx. All right. What are the critical points of that second derivative? Can the numerator ever be equal to 0? Oh, I mean, it must be a lot of complex time, but I don't know what complex time represents, right? So the numerator of this is never 0, right? This can never be equal to 0. So there's no critical points where the numerator is equal to 0. The only other thing that can happen, and what that corresponds to, numerator being 0 is sort of like, you think of that as horizontal tangent lines. If the denominator is 0, you think about that as vertical tangent lines, which are possible in a problem like this, because the function could actually be vertical at some point, right? So it's possible here to give meaning to derivatives basically being infinite. So we have to make sure that we check where the denominators are also 0, because that's going to correspond to vertical behavior. So this has a critical point at t is equal to 0 because d2y over dx squared is undefined there. This is often left out of the discussion in Calculus 1 when you're looking at critical points. The critical points can also happen in the denominators of fractions. Well, if the second derivative has a critical point at t equals 0, one thing we could do is test what the sign is of the second derivative. So I'm not actually going to make you do sign charts, but you can imagine you have a sign chart here. Here's t is equal to 0. And I want to evaluate the sign of 3/2 1 plus 1 over t squared over 2t. If I take that function and I put in something smaller than 0, like a positive or negative. Put a -1 in here. You can positive or negative out. Look at all these tools from the ancient days of calculus we're using. I pick a test point. T is -1, and I put it in. All I care about is the sign, because sign tells me positive or negative. Negative. Concave up or concave down. So when time is negative, I'm concave down. When time is 0, I have an inflection point. If I pick a test point of t is equal to 1, and I put it in here, I get a positive number. So it's concave up. I know I'm digging in some deep memories here. But that should correspond to what you see in the picture, right? Time is traveling from negative time, and notice it's concave down until we get to this point at t is equal to 0. That's what we're seeing when we see this. The inflection changes at that t value from concave down to concave up, which is the precise behavior that we see in the graph. And it's the only place where that happens. There's no more curving that happens, right? It doesn't change and tip over. Concave down, inflection point, concave up. Okay. All right, so there's your basic first and second derivatives. So we can recreate the basic ideas of calculus 1 in this setting, in a way that's very useful for physical applications, just by using the engineer's trick of manipulating these differentials. Okay, what's the next thing? What was next on our list? What's next? So we've got slope. First derivative told us about slope. Second derivative told us about concavity. What else was on my list? Arc length. Arc length. Okay, I'm going to test you. You're sitting down in your Calculus 2 final right now, and I'm your professor, and I'm going to ask you, what is ds? But what's the formula for ds? First off, is it okay if can I rate? Is there anybody that's still writing this? Can I rate it? Okay. All right, so I'm going to tell you how to compute arc length. Here, you do this. ds, the integral of ds. There's arc length. But now I need somebody to tell me what ds is. It's got a square root in it.
1.
Okay.
Plus. Okay.
dx right squared or something.
dy dx squared. That was good.
Almost. It's a d. It's an integral. We need a variable of integration. dx. Okay. Now, did you guys actually see the way the engineers manipulate this thing to get the one in the other direction? It's wonderful. We're going to do the most abusive the most awesome abusive notation here of all time. Okay. Imagine that everything listed in here. Anyway, so if you before I do that, this version of ds told you how to calculate arc length when you had y as a function of x. So when you had y as a function of x, then you integrated from x is equal to a, x is equal to b of the square root of 1 plus dy dx squared dx. That is the formula for arc length, right? L is equal to this in the case where y was a function of x. Now I'm going to do this next computation because it's cute and because it makes my skin crawl as a mathematician. It's like this is the way people do math, except that it works, and then they leave it to the mathematicians to justify why it works. So 1 plus dy dx squared times dx. Well, one thing I could do is, I'm saying equals here, but you should take that with a grain of salt. 1 plus dy dx squared, and really if that's a dx to the first power, I can think of it as a square root of dx squared. You guys chose to be scientists, not me. This is, this is your fault. Okay, well, if I've got two things under square roots, I can clearly combine them as one square root. So this is equal to the square root of 1 plus dy squared over dx squared times dx squared. And I can distribute the dx's inside. And that gets me the square, well, 1 times dx squared is just dx squared. Plus, well, now the dx squared and this dx squared cancel, and I get a dy squared right here. So if I wanted to get an expression for dy, the engineer says, or the scientist, well, I got this one by dividing out this, or by factoring out this dx. What if we factored out a dy instead? So if you took this expression and you took a square root of dy squared out of it, what will be left behind? Dx dy squared plus 1, which gets you the other formula. 1 plus dx dy squared. Well, the square root of dy squared is just dy, and that's the arc length formula for functions x as a function of y. So now here's the challenge. This guy right here, this is also ds. I haven't done anything. Still ds. But now I could write L as being the integral from y is equal to a to y is equal to b of the square root of 1 plus dx dy squared dy. So here's your challenge. What sort of mathematical BS can I do to this thing to find an expression for ds in terms of dt? Same kind of cruddy manipulation. This one's almost magical.
Yeah, totally.
Oh, I could just invent a dt that's inside this thing and factor it out. Why not? Let's just pull a dt squared out of this entire thing. I mean, after all, if I have the square root of dx squared plus dy squared, certainly I could rewrite that as dx squared over dt squared plus dy squared over dt squared times dt squared. These are just numbers after all. And what happens? Well, you get the square root of dx dt squared plus dy dt squared, and then the square root of dt squared is just dt. So there you go. There's parametric ds. And why am I showing you this? Not because it's some party trick I expect you to pull out, although I'm sure all your friends would be impressed if you showed them how to derive the parametric version of ds. But more that this kind of manipulation is how new formulas are discovered by working scientists. Right? If you can't remember a formula, you can always just derive it by pretending things are numbers. So this guy right here, this is parametric arc length. That's the ds formula we use when we're finding arc length of parametric function. And yeah, just really, I mean, this is typically the justification used for believing this is true. Is, oh, you just factor out a dt squared. Math is cheating, I guess, is the upshot. Okay. So let's write down, using our previous expression then, our previous example. Why don't we see if we can compute, here's one. Suppose that x is equal to the sine of t. Y is equal to the cosine of t. And t runs between 0 and pi. Find the arc length of the curve that is described. Find the arc length of the parametric curve. When you say arc length, the first thing you do is you write down the integral of ds. And then you choose the context that you're working in. I'm doing this now because we're also going to be looking at arc length in the polar situation later. And I want to make sure that, like, arc length is always the integral of ds, but the ds has to depend on what the context is. So we're going to be using parametric arc length because we've got parametric functions. In this case, the integral from 0 to pi of the square root of dx dt squared plus dy dt squared dt. It's a dt integral because we're working in parametric plane. All right. So if we do that computation, okay, so dx, what's x? X is sine. So what's dx dt? Cosine? X is sine, so dx dt is the derivative of sine with respect to t, which is cosine. Here, we have to compute dy dt, but y is cosine, so dy dt is minus the sine. Oh man, this integral doesn't look easy to do. The square root of cosine squared of t plus sine squared of t. What am I ever going to do? I don't know how to integrate a square root of things that look like that. Oh, that's right. I remember the fact that I have to remember this trig identity. And every time I see cosine squared plus sine squared, it's 1. Is this a trick that your math book likes to use? Yeah. Making easy integrals out of hard integrals into easy ones by using trig identities? Absolutely. Same rules apply here as applied in calculus 2, which is it's very difficult to write these so that they work. So the typical body of work here will be in terms of these trig integrals. Okay. Okay, so this integral turns out to be t evaluated from 0 to pi, which is pi. That answer makes sense, by the way? Yeah. Why? Yeah, because remember last time we showed that this was a half circle, right? It's a half circle, and we've shown that the length of this half circle is, like, it's a half circle of radius 1, so its circumference is 2 pi, and we did half of it, so pi. All right, so that's arc length. One thing to be aware of when you're doing these arc length calculations is to imagine, I want you to imagine that we had the same problem. X was sine t, y is equal to cosine t, and t now ran from 0 to 4 pi. Without computing anything, can you tell me what is going to come out of this integral? This integral corresponded to going around a half circle, to going around the circle halfway around, right? This was a circle and we went halfway around, and the arc length here said the length that we did was half of the circle. How many times am I going around the circle now? 2 times all the way around, right? 0 to 2 pi gets me once. 2 pi to 4 pi gets me around again. There's only 2 possible reasonable answers for this. That the arc length is going to tell you that the length of the circle is 2 pi, because that's the circumference, or it's going to pick up the fact that you traveled around it twice parametrically, and it's going to give you 4 pi out of the answer. What do you think it does? It's going to be, actually, annoyingly, the answer to this is 4 pi. Basically, what ends up happening is, so it's sine, so you start at the point 0, 1, you go this way. So you go around once from 0 to 2 pi. So 0 and 2 pi fall at the same point, but it also adds up the length of traveling around again. Yep. You do, right? So now I'm pointing this out not for me, but because in physical applications, sometimes it really matters. If you want to know how far the particle traveled, that's a different question than wanting to know how long the path that it traveled was. So this curve was traversed twice. So if you're interested in what the particle is doing, this integral makes sense. If you're interested in the actual, this path, then you have to account for the fact that the function came back on itself. Now, it's not always obvious that's happening. You can have weird functions like this one. So this thing follows a parabolic trajectory. In fact, I have a nice picture of this in 10.1 here. Make sure I got the square in the right place. Cycloid. Not that one. Where did they put that? Yeah, it's this one right here. This should be sine squared up here, and this is sine. What you get out when you do this is you still get out y equals x squared as the relationship between these two things. If this is x and this is y, you can plug this in to get y equals x squared. But these things are oscillating. So what ends up happening is the particle is traveling along this parabola, but it's flopping back and forth between the two ends depending on what the t values that you allow to happen are. Because sine repeats itself every 2 pi, right? And so the sine, as t goes from 0 to 2 pi, this sine bounces back and forth between -1 and 1. But that means that like you're traveling along this parabola over and over and over again. And if you just want to know how long that chunk of the parabola is, you have to account for the fact the particle is repeating itself. So yes, obnoxious, but important. Okay, so the last thing I guess I want to talk about next time. I don't want to push this. You know what? I don't actually need to go much further than that. I will say that like the next thing I want to talk about is area. So we'll do this in more detail next time. You guys can guess how much time do I have? None time. Okay. So what I want you to think about, I don't want to read ahead, is we know that the area under a curve, the way we learn the fundamental theorem of calculus, is that if I have some function f of x, and I have an a and a b, and I want to compute the area underneath f of x, the way I did that was a is equal to the integral from a to b of f of x dx. We should be able to do this same computation where that curve is defined parametrically. So if you really want to challenge yourself with this loose engineering type thinking, think about how you would take this and reinterpret it as a dt integral instead. That's what we'll talk about next time. Is we've worked with derivatives, but we haven't started working with integrals yet. So we'll talk about how the integral formulas change underneath this parametric setup as well. All right. Sorry about the heat. See you guys next time. No, man, this is calculus. Everyone was people have been telling me they want to get back to calculus. Boom, we're doing calculus.
But I don't like that.
I like this.